The first scene we included is a salute to the competency and professionalism of the engineering support and launch control team at the Kennedy Space Center. On March 22nd, we made our first launch attempt, but due to a leaky valve, the right engine didn't come up to full thrust, and that shut down, as you can see in the film. The other two engines shut down, and the calm and coolness of the launch control team led to safing the vehicle and expediting the egress from the vehicle at that point.
Well, we put the delay to good use and focused a little tighter on our mission and the objectives and got a second shot at it a month later. Beautiful weather, on-time launch. Here you see 3 good engines coming up to full power for 6 seconds. Signals the boosters to light. And at the liftoff, we got 7 million pounds of thrust pushing 5 million pounds of vehicle into orbit, and the experience of a launch is spectacular. It really is something. We had trouble-free ascent all the way to orbit, and here in first stage you'll see us penetrating a little bit of cloud layer that was very, very thin and not a problem for us at all. But what you'll see as we approach the region of maximum dynamic pressure here, the vapors form around the nose cones of the solid rocket boosters and the orbiter itself. Then as we get to about the 2-minute point in the ascent, the solid rocket boosters burn out and separate, and we get a bright flash of orange across the windscreen that we can see from the cockpit as the boosters separate. Another 6 minutes, we're in orbit.
Shortly after getting into orbit, I launched downstairs. I was very quickly got out of my seat to come upstairs to do some engineering photo documentation of the external tank. The tank looked like it had fared the launch in good shape, and we got some excellent photographic documentation for the engineers here on the ground. After the doors were open, we had our first opportunity to look at our home for the next 10 days. You see the Space Lab there in the orbiter's payload bay. And you also see us now coming into the Space Lab through the tunnel that connects between the orbiter's middeck and the Space Lab. Within about 3.5 hours, 4 hours after we got onto orbit, we were already starting to activate the laboratory. And here's a view from the aft end-cone camera as I'm activating the systems, and Dr. Volter's coming in to assist me in that project. We were very busy on orbit. We had 88 experiments to conduct, and while we did work on 2 different shifts of 12 hours each, there were periods of time when all 4 of the payload crew members were in the laboratory conducting experiments, and this gives you an impression of the very busy schedule that we had conducting all those experiments.
Out of the 88 experiments that we had on board, 40% of it involved human studies in human physiology. Here you see me doing an echo on myself, and that allows me to image the heart so we can determine heart function and volume. We also did a number of other tests. Included in that were saline infusion. You might have read about that in the papers, that we infused up to 1 liter or so of fluid in our bodies. It was mainly as a test and not as a operational replacement of the fluid that we lost going into space.
Well, in order to keep the blood from coagulation, Bernard is now putting me a small amount of saline liquid into the catheter, and after that it will be centrifuged in a centrifuge, which is currently done by Jerry, which takes about 10 minutes, and the blood plasma is separated from the rest of the blood, and after that it's put in the middeck for cooling down to very low temperatures. Also, the metabolism of the body is changing in weightlessness, so here a mass spectrometer analyzes the breath of Jerry's exhalation gases in order to figure out what the difference is between micro-G and ground.
Here I measure the thickness and compliance on the skin of my forehead, and micro-G makes a fluid shift to the upper body. And where does the fluid go? Does it go into the skin, and if into the skin, into the cells or between the cells? Everything else in space changes too, and especially the effectiveness of our metabolism and of our lung. We investigate that by doing several different breathing maneuvers under rest and under a defined workload, like here on an ergometer.
Here you see Charlie Precourt conducting an experiment called baroreflex. And it's actually a way in which we can apply positive and negative pressure to the neck, and that causes the heart to react in a certain way. And actually, we study the reflexes of the heart, the ability to increase the heart rate and decrease the heart rate in terms of response. We also had a number of biological experiments on board. Here you see me conducting one of those experiments in a foldable handling box. This allows us to fill chambers with electrolyte fluid without the fluid escaping into the cabin, so it helps us to contain that. The next scene here is showing you one of those growth chambers, which are plant roots. And as you can see here, we had to show this to the ground several times during the flight. You can see a number of the roots, how they grow either upward or horizontally, and that really is dependent on gravity. And so you can kind of see that, and we made measurements of that.
Here we see the swimming pattern of young tadpoles and fish. And during the mission we observe how that behavior changes, and then we take these species down to Earth and look at the individual changes of their vestibular organ and the neurological changes. After taking pictures of these young and healthy mushrooms, at different times, we take samples, fix them, and take them down to ground. So further analysis can be done by different kinds of microscopy.
Well, one of the major objectives of the biological experiment was the fusion of cells in order to combine two traits of different plants into one cell. And here you see the alignment of these cells in an electric field. A high pulse of electric fields will make the cell fuse, and you see two of these cells fused on the left up corner of the picture. And after that, the cells are fixated and put at very low temperature, about -300 degrees Fahrenheit. And you see Bernard putting it into this liquid nitrogen to keep it cool for further analysis on ground.
This is the robot technology experiment. We have two different cameras, one in the grip of the robot arm and one, as seen here, in the work cell. We look at these pictures on a TV monitor via glasses to have a stereo image. And we're doing different tasks. The most sophisticated one which is shown here, catching of a free-floating part.
We had a total of 7 different types of furnaces on board in 2 different facilities. We would use those to melt around 3 dozen different samples of various compositions. And then we would allow those samples to re-solidify. And what we were really trying to study is the basic physics of what's happening when those melts re-solidify, and also then to bring those samples back down to the ground and understand the physical properties after those samples have been processed. The next view, you'll see us looking internal to that furnace that Hans is working on there. This is after the furnace has already been heated up to the point where the sample is melting, and it allowed us to judge the sample and to alter the process as we were watching the melt in real time.
This is a fluid physics module. Only under micro G we are able to grow big, self-containing liquid columns. And we are looking for their stability, their resonances, and for different patterns of internal flow. What you see here is the growth of one of these liquid columns in a time-compressed way. And here we see some oscillation.
Here I'm preparing for another fluid physics experiment at a higher frequency of the column in order to run through the resonances here in the microgravity environment. We're also going to the limit of the breakage of the column, which is called the Rayleigh limit, and you see it happening right now where you get to the limit where the column breaks into parts.
This is a picture of another facility that was used to study fluid physics called a holographic laboratory, which we use a hologram to document the current flow. You can kind of see the current there. It's called Marangoni currents, and basically studies surface tension versus temperature of fluids.
Take a look outside the module now at some remotely mounted instruments, the Shuttle amateur radio antenna, the Gauss camera for studying the Milky Way, And the mom's camera, you see here that did stereoscopic mapping of the Earth. We also had a gas can out there for some material science and an atomic oxygen exposure tray.
The only significant anomaly we had on the mission pertaining to the orbiter was a small hole that developed in our wastewater tank, which was leaking nitrogen. You can see the hole at the end of the pin. We were able to coordinate an effort with the ground, enabling us to cap off the nitrogen flow to that tank and then connect our wastewater flow to a contingency waste container, essentially a canvas bag. And that enabled us to stay on the orbit for at least, or in orbit for at least another 6 days. However, to stay for the full duration, we needed to be able to dump the contents of that bag, and that's what you see here. And this is the flow out the window, the ice crystals forming in space. And that was successful and enabled us to stay up for the full duration.
We had several major press events during the mission, and one of which you see here was a 30-minute one with questions answered to reporters back into Germany and Europe, coordinated with the GSOC, or the German Control Center. We also flew a SARX, or an amateur radio, on board. Here you see me talking on that radio, and we conducted at least, I believe, 14 contacts with schools, answering the questions of school children.
Another thing we did with the SARX was to conduct a test comparing the two antennas, the standard orbiter SARX antenna with that SAFEX antenna I showed you on the module a minute ago, and that was what turned out to be a very successful test for the SARX program. Here's to give you a view of what it's like in our sleeping arrangements. I'm waking up the blue shift to get them started on another day work in the lab, and we get them roused up, and at the same time the red shift's preparing dinner to get ready to go to bed. We've got Steve here shaving, getting ready for breakfast. It's a busy time when we have crew handover, and yet it's one of the few times, because of our busy schedule, that we can get together for dinner and talk about the events of the day and do a little bit of filming of our eating habits.
Exercise is important on orbit, just as it is here in 1G. And the next scene is myself riding the ergometer on the flight deck in support of a medical experiment to determine the benefits of intense exercise the day before landing.
You don't get away from paperwork even in space. And we had our own fax machine, and we were uplinked over 230 messages, which when cut into separate pages constituted over 600 pieces of paper, and we read all of them.
This is a very small pocket experiment where I experienced the amount of the magnetic field, Earth magnetic field, even in space. I put a small magnet which will interact with the Earth magnetic field and start to oscillate in that field.
Well, this scene probably needs to be put to music rather than my narration. And it was on our last day before closing up the lab that we had a little bit of time to experience zero-G aerobatics. And about all I can say here is that zero-G is a delightful place to live.
Well, we hoped that our photography would be more spectacular than Charlie's dancing. And to support that, we had over 20 cameras using 6 different formats. We captured over 6,500 still frames and literally days of video.
The next scene is crossing the Persian Gulf, looking down the Gulf in a southeasterly direction around the Strait of Hormuz into the Gulf of Oman. And we passed this area daily and caught some spectacular still photographs as well as movies.
And every morning as the red shift came on duty, this is what was passing under us on the Earth, the Himalayas. You can see in the foreground there the snow-capped mountains. And just coming into view on the far right side of the screen now is Mount Everest. And that was a really incredible way to start your day.
For a micro-G laboratory, it's important to know how micro-G disturbances propagate through the lab and appear at different sites. And so what we did, we applied micro-G disturbance by hammer blows, very well-defined ones, and looked at different places with sensors, how high or how big the G jitter really was.
On the day before entry, we checked out every primary reaction control jet by firing them, and here you see some of the tail jets being fired. And after that, we got into the flight control system checkout, in which we checked out basically the entire flight control system, all the sensors, nav aids and displays. And I think it's worthy of note on an airplane as complex as the Columbia is, we had absolutely no anomalies in any of these tests at all.
Once the checkout was done, it was my job to deactivate the payload and also the space lab. And you see me here closing the airlock to the space lab in preparation for deorbit prep.
Once the work in the lab was finished, we had a few moments to reflect upon the mission and the successes that we hope to achieve later on the ground with the data. We were also able to try and capture some of the beauty of space flight, and this is a real-time sunset, and they were spectacular on this mission, as well as the moon rises and sets.
And with a successful laboratory mission behind us, it was time to get suited up, strapped into the seats, and get ready to come home. Of course, as you're aware, we waved off to the Kennedy for weather and ended up going to Edwards. And Jerry was able to capture some of the glow from the plasma of heat of reentry around the orbiter as we came in on the night side. But we were approaching a sunrise, and you'll see here in a moment Tom's window on the right-hand side of the vehicle is orange right there, while the sun is rising through Steve's window. Really spectacular.
Of course, we diverted into Edwards after getting an extra day and an extra orbit out of this mission, and we flew to a left-hand turn, about a 180 or 190 degree turn left to runway 22 at Edwards. We flew down a 17-degree glide path at 300 knots to about 2,000 feet, then flared onto a shallow glide path. Tom lowered the landing gear at about 300 feet, and we continued to decelerate and descend and touch down about 2,000 feet down the runway. From the point of touchdown until where we lowered the nose, you've got some slowing down to do down to 175 knots. So the nose stayed in the air for a little while, and then when we derotated or lowered the nose, Tom deployed the drag chute. And my perception, I think everybody's perception, was we didn't really feel the drag chute come out in its reefed configuration like you see right here, but when it disreefed or fully opened, we felt a good strong tug and a deceleration. And from that point, we just applied light to moderate braking and rolled to a stop. We used about almost 12,000 feet of the runway, but could have stopped a lot shorter. The drag chute is jettisoned at 60 knots so that the risers won't lay over the engine bells of the main engines when you come completely to a stop. And this signified the ending of what we consider to be a very successful mission. And I'm very thankful, as I said before, to have had the privilege of flying on this mission, to have worked both with our American friends and our German friends. And we all have a sense of fulfillment. Here they are thanking me for getting them back on the ground, I guess. But we all have a sense of fulfillment from this mission, of having participated in something that was meaningful, that was accomplished only with a lot of hard work.
And coolness of the launch control team led to safing the vehicle and expediting the egress from the vehicle at that point.
Well, we put the delay to good use and focused a little tighter on our mission and the objectives and got a second shot at it a month later. Beautiful weather, on-time launch. Here you see 3 good engines coming up to full power for 6 seconds. Signals the boosters to light. And at the liftoff, we got 7 million pounds of thrust pushing 5 million pounds of vehicle into orbit, and the experience of a launch is spectacular. It really is something. We had trouble-free ascent all the way to orbit, and here in first stage you'll see us penetrating a little bit of cloud layer that was very, very thin and not a problem for us at all. But
the first scene we included is a salute to the competency and professionalism of the engineering support and launch control team at the Kennedy Space Center. On March 22nd, we made our first launch attempt, but due to a leaky valve, the right engine didn't come up to full thrust, and that shut down, as you can see in the film. The other 2 engines shut down, and the calm.
What you'll see as we approach the region of maximum dynamic pressure here, the vapors form around the nose cones of the solid rocket boosters in the orbiter itself. Then as we get to about the 2-minute point in the ascent, the solid rocket boosters burn out and separate, and we get a bright flash of orange across the windscreen that we can see from the cockpit as the boosters separate. Another 6 minutes, we're in orbit.
Shortly after getting into orbit, I launched downstairs. I was very quickly got out of my seat to come upstairs to do some engineering photo documentation of the external tank. The tank looked like it had fared the launch in good shape, and we got some excellent photographic documentation for the engineers here on the ground.